Algebra 2. Happy Thursday. We've talked about polynomials in 3.1. Next section, 3.2. We're going to look at the graph and analyze some of these polynomials. All right. Pause if you need to. I got a little learning target there. We're going to specifically talk about intercept form of our functions here. All right. So we've seen standard form before. Today we're using intercept form. Success criteria today: if you can sketch a graph of a polynomial function from intercept form, or use a graph to write a function in intercept form. All right, we're going to talk about all this in just a second. Pause if you need to. Okay, intercept form here. Again, we saw standard form where you had all of your terms being added together. Here in intercept form, we have these little products, all right? These things being multiplied together. So we could say that a polynomial p of x is equal to, this is just the general form. Maybe there's a constant being multiplied out front. I mean, maybe I multiply by 2 or multiply by -1, right? So there could possibly be a constant out front. And we see all of these little linear factors, or what we're going to kind of call them. I'm going to call them the chunks of our polynomial, informal word, but you get it, right? We've got a chunk here where we have our variable x minus a number, a constant number, a1. I don't know what it is. We're just going to call it a1. Here's another chunk, x minus a2. There's our second linear factor. And maybe you have n linear factors, right? We'll see an example of this in just a second. So again, that x, the x here, x and x, those are your variables, right? If you wanted to evaluate a function, you could just plug in a number into those spots where you have variables, and then c, a1, a2, a3, a4, dot, dot, dot. Those are just real numbers, right? They're constants, they're parameters, right? So the x-intercepts, which is just a fancy word for zeros. You remember we talked about zeros in mod 1. A zero is a function, or a zero of a function is where the graph crosses or touches the x-axis. It's also what we call x-intercepts, right? Because they intercept the x-axis. The zeros, or the x-intercepts of your function, can be pulled right from your intercept form. And we'll see an example of this here in just a second, but if you looked at this intercept form, you can identify a zero right here. If you have x minus some number, boom, there's an x-intercept, a1. Hey, here's another x-intercept, a2, right? It's part of my linear factor here. I can pull out those parts. Pause if you need to. This would be a good example to get down. Okay. Look at this polynomial. It is currently written in intercept form. We see these linear factors, the chunks of our polynomial, right? I have x minus 2, and I have x plus 3. I'm going to show you we can really quickly put this thing into standard form by just foiling this out, right? If we multiply this all out, well, that's going to be x squared plus 3x minus 2x minus 6, right? All I did was just FOIL it all out, and check it out. This simplifies down to f of x equals x squared plus x minus 6, and that's my polynomial in standard form, right? So we can kind of go back and forth between these. You could factor this out, or you could FOIL this out to go back and forth between standard form and intercept form. Okay, so what did we just talk about? We can take this intercept form and find the x-intercepts right from here, right? We can find the zeros. When you think about zeros, those are the values, again, where your function crosses the x-axis, right? It's the values that make the function equal to 0, because right here, right there where it crosses the x-axis, your value there, it's a positive 2, but your y value is 0, right? Again, over here, my x value is a -3, but my y value is 0. That's why we call them zeros, right? So if you took positive 2 and plugged that into your function, that would be 2 minus 2 times 2 plus 3. 2 minus 2 is just 0, right? So that value that we see right there, our x-intercept, which is right there again, 2, that positive 2 is the number that's going to make this part equal to 0. And then 0 times any number is just 0, right? So that's one value that could be considered a 0 of our function, an x-intercept. Another possible value, because we see it crosses twice, is negative 3. And where are we getting that from? Well, we're getting it right here. You could write this linear factor, this chunk of our polynomial, you could write x plus 3 as x minus a negative 3, right? And hey, we were talking about x-intercepts. There we go. We can see x minus a number. There's our x-intercept, our 0, which is at negative 3. Or you could say, what value is going to make this equal to 0? Okay, well, if I took x plus 3 and set it equal to 0 and just solve, minus 3 from both sides, hey, x is still equal to negative 3, right? So we can kind of see that a couple different ways. So basically, this is what we're doing basically. You look at the first chunk of your polynomial, see how it's a negative 2, it's x minus 2. So we're going to flip it and say, okay, my 0 is a positive 2. And that's where we see it cross at positive 2 there. Or you look at your next chunk, another 0, see how it's a positive 3? Just think opposite, right? So negative 3. And hey, definitely right there, there's our negative 3. We could find negative 3 by setting this little chunk equal to 0. So those are the two values of, those are our x-intercepts of this graph. Okay, let's take a look at a couple more vocabulary terms. Some of them are new, some of them are very similar to what we've talked about before. A turning point is just the part in a graph where it changes from increasing to decreasing, or vice versa, so from decreasing to increasing. If you look at that example over there that I've graphed, I can definitely see two turning points. One of them is going to be right here because we're increasing, I hit that turning point, now I'm decreasing for a little bit. I hit another turning point, okay, I was decreasing, that turning point hits, now I am continuing to increase, right? That's basically what turning points are, is you're literally turning. So your global minimum or maximum is a value that is greatest or least for all values. And as we see, what we just kind of touched on right here with our turning points, we're going to be looking at these maximums or minimums and kind of classifying them as turning points or global maximums or local minimums, right? So if we tried to pick out some maximums here, well, there's definitely a maximum here. Again, that was a turning point that we just talked about. And then there's definitely a maximum here because it kind of stops. So we've got these two ideas of maximums. The global maximum is the biggest one, right? So this is obviously a bigger maximum than this one here. So this is your global maximum. Your local maximum is a max for all other turning points in our graph. So while this one was considered the global maximum, this other turning point it's a maximum, but we're just going to call it the local maximum, right? Same thing for global and local minimums, all right? So on this example, I definitely have this global minimum here. I have another minimum, which is going to be considered a local minimum. I'm getting tired of saying that word. It's local because it's not as small as this one, but it's still another turning point where we see a min in our graph. Pause if you need to. Another little fact here. The number of turning points Could be maximums, minimums, global maximums, etc., right? The number of turning points in our graph has to be less than the degree. So if your degree is n, you can have at most n minus 1 turning points. So let's say you have a quadratic. I'll sketch it out real quick. Let's say you have a quadratic, maybe it looks something like this. It's got 1 global minimum. It's also considered a turning point. I know that my quadratic has a degree of 2. All right, well, 2 minus 1 is just 1. So indeed, I have at most 1 turning point right there. Might be a good little sketch to get down. We're going to look at the example that we just talked about earlier. So again, we're back to here with our function f of x equals x minus 2 times x plus 3. It's in intercept form, right? If we had to identify a turning point, boom, right there. It's also a global minimum, right? And this thing has a degree of 2. If I factored all of this out, right, we saw that we had x squared plus x minus 6. This thing has a degree of 2, so it can have at most 1 turning point. Again, we see that right there, right? I can see the degree from standard form. I can also kind of see it from intercept form, because I know eventually if I'm going to factor this, or excuse me, if I'm going to FOIL it all out, right? Multiply the x times the x, multiply the x times the positive 3. If you keep doing that, eventually you're going to have an x times an x, right? You've got 2 x's in there. Eventually you're going to have x squared. So I can see since I have 2 x's there, my degree is also going to be 2. Okay. Okay, look at this next function. It's an intercept form. We can see all of these little chunks of our polynomial, right? And we can identify some global maximums and global minimums. So I'm going to look at this point right here, which is definitely a local minimum, because I see that this thing, it's going to keep going up and up forever and ever. So I know I have a global max that is positive infinity. I have a local maximum because it is a turning point. Maybe that's about at 40, 41. I'll call it about 40. I have a global max at about 40. Still, again, definitely smaller than positive infinity, right? So that's why we call it just a local maximum. If you look here, I have another local minimum, and I have a global minimum as this continues to decrease. So it's going to continue to decrease towards a negative infinity. So that's what our global minimum is going to be. And then I can say that that local minimum, I'll say maybe that's at about -5. All right, let's look at those x-intercepts a little closer. Okay, I have zoomed up on this image now. We can actually see our x-intercepts. There's one here, there's one here, there's one here. So let's look at the linear factors, each little chunk of our polynomial in intercept form, and make sense of them. So the first one is x plus 4. If you wanted to figure out what value of x makes that equal to 0, well, just set it equal to 0 and solve for x, right? So x equals -4. And we see that that x-intercept definitely is at -4. Okay? And again, it's similar to what I said before, right? You just look at this thing and say, okay, I see a +4. The opposite of +4 is a -4, right? So look at the next little chunk of your polynomial. I'll highlight that in blue, x minus 3. You could set that equal to 0 and solve for x, and I'm going to get x equals +3. Or you could just look at this here, right, and say, okay, I see a -3. Opposite of -3 is a +3. And hey, check it out. That's one of our x-intercepts that we have graphed. Look at that last one there. Highlight it in yellow one more time. X minus 2. I see a -2, so what's the opposite of -2? it's a positive 2. There again is another x-intercept. Or you could find that by doing x minus 2 equals 0. What value of x will make that chunk of your polynomial equal to 0? Add 2 to both sides. Again, we still get that x equals positive 2. We also know that this is a cubic function, because eventually if I had to if I had to FOIL all of these out, I see that I have 3 x's. Eventually I'm going to have to multiply all of those together, and you would have an x cubed as your first term in your standard form, right? So already I can tell you that the parent function of this, which is right here, right? The parent function of this thing is a cubic function because the degree of this thing is 3. Again, we have those 3 x's. If we had to multiply all that out, eventually you would have x to the 3rd power as one of your terms. Okay. What is this quadratic in intercept form? So let's see if we can take the graph and write the function for it. I know it's a quadratic. I know it's going to have a degree of 2. It's probably going to have 2 of those linear factors, right? 2 little chunks of our polynomial. So I'm just going to kind of fill this out now, right? It's a quadratic. I've got 2 chunks of my polynomial. Let's take a look. I have one intercept that is at a -1. So if you think opposite of -1, my linear factor here should be x plus 1. And we could check that. Is -1 a value that would make this little chunk equal to 0? If you plugged in -1 into x here, you're going to have -1 plus 1, which is just 0. So check mark, yeah, that works. It's an x-intercept. Okay, what about this other place where it crosses my x-axis? Crosses at a +2, so what's the opposite of +2? A -2. So this intercept, x minus 2 for that last factor. Pause if you want to get that example down. And there's one other thing that I forgot to mention at the beginning of the video, so make a little note at the bottom of your notes here. If you have x-intercepts that cross the x-axis, for example, it crosses here, it crosses here, those are called, they're crossing intercepts. There's another special word. If your x-intercept, it just touches the x-axis. So for example, if you had a function that looked like, I'll do it in red so you can see. If you had a function that looked like this, we have a crossing x-intercept there. We have another crossing x-intercept here, but check this one out. It doesn't cross, it just goes up. It touches the x-axis and then it goes away. So since it technically doesn't cross over, this one is called tangent. All right? Possibly a word that you remember from geometry last year. So that right there is what we call a tangent x-intercept. These here are just called crossing. All right? Pause if you want to get that little example down. And real quick, hey, turning point, a turning point. And we could even classify these. That's a global maximum, that's a local maximum, and that is a local minimum. All right. I'll see you in Blackman 107 to check off some notes about intercept form. We'll have some review. Please participate. Get excited.